And let me start. I know some people here are very familiar with a lot of what I'm going to say, maybe already heard my talk, and some people are further away from the area. So I'll try to give you a background maybe quickly. If you want to know more about something, please ask questions, especially as this is a small group. So what is this going to be about? I'm going to study transverse knots and lengths in a contact manifold. For most of the time, my contact manifold is just going to be a 3-sphere, but more generally, everything is in a 3-manifold equipped with a contact structure, which is the kernel for one form, which satisfies this non-degeneracy condition. So this simply means that we have a non-integrable plane field. Orientable. And my basic example that I'm going to work with is this standard contact structure on S3, which is given by this one form in polar coordinates. So the picture for this is just that when you go along the z-axis, you have horizontal planes, and as you go on the radial lines, your planes turn sort of to being vertical at infinity. Okay, and if you are in a contact manifold, if you have a contact structure and you want to look at knots, then you have two kinds of knots, essentially, two kinds of interesting knots. One interesting thing is looking at Legendre knots that are tangent to the contact structure, and this is a wide topic, a big topic studied in symplectic geometry. There are a lot of invariants of Legendrians. This is important. Another special class is transverse knots that are transverse to the contact structure. So I'm going to say that my knot length is transverse to psi, and this turn out to be pretty interesting as well in dimension 3. Okay, and I said that this is going to be related to braids. Why so? Well, first, in this picture, you can see that if you make a braid around the z-axis, braid around z-axis gives you a transverse length. You know, if you pull it out to infinity and kind of perturb it slightly, it's going to be everywhere transverse to psi. And conversely, what's well known in the field is that every transverse length in this contact structure can be represented as a braid. Be represented as a braid. When I say represented, I mean that you can isotope it so that it remains transverse to the contact structures and it becomes braided around the z-axis, right? So this is kind of a contact version of the classical Alexander theorem. Every knot can be made into a braid. And moreover, you sort of know what kind of braids represent the same transverse knot. So two braids are transversely isotopic if and only if, maybe two braids, K1, K2, if they are related by braid isotopies. Obviously, braid isotopy preserves this transverse thing. And a special move, which is a positive stabilization, which means that you're adding an extra strand to your braid. This is the braid. And you say, I'm going to add an extra strand and make a positive crossing. Positive stabilization, and of course destabilization is also allowed. You can go that way. The sign of the crossing is very important. If you put in a negative crossing, you've changed your transverse class. Okay. So then it really means that up to this stabilization, you can study transverse knots in terms of braids, and you can ask, well, what kind of contact geometric properties are seen by maybe the algebra of the Braid words, or maybe the monodromy of the Braid as, considering its action on the punctured disk. So this is the kind of questions that I'm going to discuss. Okay. Now, I said what kind of transverse properties, then you can ask, well, what is this Legendre transverse knot theory? How is it different from the usual topological knot theory? What kind of information is there? And of course, first you can say there's a topological type of knot. Second, there are some basic algebraic topological invariants. So I will give you an invariant self-linking number for the transverse knot in a moment, but just an example, if you have a Legendrian knot, then contact planes give you a framing, right? And this is an invariant that you can look at. And beyond that, there's really a lot more that's happening. And for Legendrian knots, this is again a big theme that can be studied via contact homology, via DGAs and stuff like that. For transverse knots, it's actually remained a tricky question for quite a while, and then the first invariants that could detect this subtle information were given by Oshwood and Sabo and Dylan Thurston, actually quite a while ago, I think around 2008. And that was a combinatorial construction by a grid diagram. Combinatorial knot for homology. There's still a word Flora here because this is a version of Hegel-Floer homology, which is related to holomorphic curves to begin with, but then it admits a combinatorial description. So combinatorial knot for homology, and this gives a transverse invariant. So this is this last word in my title. I'm going to describe how this invariant is actually system geometry related to the knot, as opposed to just detecting that the knots are different. So maybe before I go to the definition, let me say that this is something that I will denote by theta, lives in some knot-for homology group, and it can be easily computed, and if you know where to look, there are examples such that they are smoothly isotropic, and this algebraic topology information is the same, but the invariant maybe for one knot is 0, and for the other knot is non-zero, just because you've computed it by the computer and you sort of see, okay, these knots have to be subtly different in this very special way. But like, what does it mean that the invariant is 0 or non-zero is something that I would like to talk about. Okay, maybe before I go to the next board, let me define the self-linking number for transverse knot, which in the Braid setting is given by the number of positive crossings minus number of negative crossings minus the Braid index, which, if you believe what I just said about the braids, you can check that if you add the stabilization, that this formula gives you the same answer. So this is indeed okay. Don't look at this picture yet, but this is an example of a grid diagram. And before we go to that picture, to the end of my talk, let me just quickly give the basic definition for people who know grid homology. I just want a fixed notation for everybody else. If you don't know, then maybe just a quick picture of how you build this. So, knot for homology. I start with a knot or link, and I want to build what's called a grid diagram to encode this link in a picture like this. So the construction of the Oshwood-Szabo theory gives you invariants for knots and links, and then the combinatorial definition is due to Manolescu, Oshwood, and Sarkar. So what do? well, maybe I'll start with the Hopf length. And I want to make it into a braid. I want to look at the version that works with braids. So I will draw it like this. Just kind of put it in this form. And then I want to kind of make a square picture out of this. So I will make it like this. Okay. And then from this, I can sort of put the corners, mark the corners of where the strands turn in a picture, and I can get something like this. So how does this encode my knot? Well, I just say so I got the length that I started with, got the braid that I started with, and more generally, if you're given a picture like this, well, how do you go from a diagram to a knot? You connect, so grid diagram. Grid diagram is a picture like this or like this that has exactly one X and one O in each row and column. And then what you do to reconstruct the knot is connecting X's and O's horizontally, like this. And then vertically, because I want to make a braid, I connect X's, O's within the diagram. And if I have X above the O, then I connect like this so that I get a braid picture. And also the rule is that horizontal strands crash over the vertical. So again, I know to some people this is very, very familiar. If you have not seen this before, any questions? So we got a grid diagram starting from a knot. And now to define a chain complex going from the grid diagram, the generators will be, if this is n by n diagram, the generators will be n tuples of grid intersections. So these are not inside the grid cells. These are really kind of these points like this, and tuples of grid intersections, one in each vertical and each horizontal row. I have to say that the diagram is considered as living on the torus. So we say the top and the bottom actually the same, and this line and this line are the same. This is my picture. And again, this kind of comes inconvenient because the red points give you just one of the generators. Right? So the generators are given by this. The boundary map, the differential, counts empty rectangles in the torus and the toric diagram. So again, what do I mean by this? If I want to compute gx for some, maybe x is not gz, for z being one of the generators here, one of the points here, then what do? I look at all ways to change 2 points in the picture in the n tuple for z to something that forms a rectangle, so that this rectangle in this configuration does not contain any axes or rows or other generators. This is what's meant by empty. Okay? And then we count these and count all ways to go from z to some other point. So this is z, this is. All right. For the experts, I should say, you probably notice I'm doing something wrong. I'm not really defining HFK hat, which is one of the flavors. I'm defining something that's called HFK twiddles sometimes, and this is actually not invariant. It depends on the size of the diagram, but the invariant could be destroyed, could be extracted from this. So if I compute homology, or I get the chain complex. So if I compute homology, I get something that depends slightly on the size of the grid. But that's all right. That's what I want to do. And now I said we want to define something for transverse knot, this transverse invariant. And now pretty much everything is in the picture. I start with a braid because I've described that transverse knots can be given by braids. I go through this diagram, and the invariant is going to be a distinguished, so theta is a distinguished cycle in the chain complex. And the distinguished cycle is given by choosing the grid intersections that are related to these X markings that are the upper right corners of the axis. And then somehow, by some magic, it turns out that this is really an invariant, that it does not depend by the braid that you've chosen to represent your knot, and then it also does not depend on how you made your grid and everything else. So this is the definition of the invariant. Okay, and again, for the experts, I am defining something which is not quite an invariant, so maybe this is like theta twiddles, but I'm only concerned with vanishing and non-vanishing properties of this, and in vanishing and non-vanishing for the hat version, which is really a bona fide invariant, is related to vanishing and non-vanishing of this guy. Just a little bit easier to compute when you only look at the empty rectangles. Okay. So now that we've seen the definition, you see that this is completely mysterious. Well, I'll go through its magic, and then how does it know that the two transverse knots are different? Well, just go in and compute. Okay, but why? What does it see? What does it mean that one invariant could be 0 and the other non-zero? I'm actually working with Z12 coefficients. Maybe to make this easier. Okay. I have to say, after this definition came up, there were some definitions for the same thing, essentially. The definition due to Liska or what Stipchich and Szabo, that who define the same invariant not only in S3 but more generally in contact manifolds via construction that uses open books. So that's a little more topological, but again, maybe also slightly mysterious. And then there's another construction by Baldwin and Vertesh in Tel Aviv, who related this open book invariant to this, showed that it's actually the same, and along the way they introduced a way to compute this invariant via braids, which is closer to what I'm talking about, and then it is a little more geometric. But still, I think it's not entirely clear what it means that you are vanishing or non-vanishing. So now I want to say how the vanishing or non-vanishing of theta is related to the braid monodromy, and I have to say that the monodromy and sort of the direction of twisting of the monodromy is a big theme in three-dimensional contact topology. And probably many people here know there's a theory of open books that is due to Giroux, and that allows to represent a contact manifold by pretty much saying that the contact structure is looking similar to a vibration associated to a certain phi but not. And then the monodromy of this vibration, the direction of the twisting, tells you a lot about whether your contact structure has certain properties, whether it's rigid or flexible. I don't want to go into this for people who are far from contact geometry, but just want to mention that this is a familiar topic. This right weir and non-right wearing theme in contact geometry is due to Honda, Kazes, and Matic. And so I sort of want to do the same story for braids. And so let me define this. Let me now look at the monodromy of a braid and define this twisting, right wearing, not right wearing twisting. heater here is actually not strategically located, maybe in the back of the room. All right, so now let's see. We have a braid which has n strings, an element of the braid group on n strings. And I can think of it as acting on a disk with n mark points. And I want to say, how do we talk about the monodromy sort of twisting to the right or not twisting to the right? Let's say that beta sends an arc going from the boundary to one of the mark points, sends an arc E to the right of itself, if, well, either beta of A is just isotropic to A, this is allowed. Or if you look at, or if you pull toward A and beta of A, you will see that, well, one arc beta of A is physically going to the right. So this is beta of A. And this is, right? So I said full toward, what do I mean? Well, the thing is, if you just look at arcs, everything is defined only up to isotropy. So I can always say, well, maybe this is going to the left a little bit. And then out here. So full toward means eliminate all inessential intersections. And after that, you can compare the tangent vectors at this point, at the initial point, which is in the boundary of the disk. Okay. And so we say that beta is right veering if every such arc goes to the right of itself, and beta is non-right veering if some arc goes to the left. I guess I haven't defined go to the left. Go to the left means does not go to the right. Well, because the thing is, you have to say that if the identity map is right veering, it's not entirely symmetric. I cannot just turn around the definition. Okay. And in fact, the proposition that I should probably say it's known that for non-right veering braids, the invariant thing vanishes. It's some version of this is in Bolden Verteshevich paper, although their definition is slightly different. So I don't know, it's an easy fact anyway, we will see the proof later in the talk, but it's sort of, I should say, it's known. And it's somehow known that for non-right veering braids, other invariants, this invariant that I defined in common homology a while ago, this is also 0, and this is due to Bolden and Grigsby. Just sort of everything vanishes, but it's more interesting to ask, okay, what if you are right veering? Can you say that something does not vanish? Maybe this veering, right veering, non-right veering, actually determines vanish and non-vanish. And this is, at least the partial answer to this is the theorem that I'm going to explain. Okay, so if the first part is that if the K is just a 3 braid, then if K is right veering, this implies that theta is non-zero. And I don't quite have the same statement for higher index braids. and I don't have counterexamples either, so it's kind of still mysterious if your right variant does this mean that the invariant does not vanish or not. But I can prove non-vanishing if I can control the amount of positive twisting, if I know that this is more than something. So let me say that C is something called fractional twist coefficient. Again, some of you probably know what this is. If you don't know, I'm not going to tell you. I'll just say that this measures, roughly measures the amount of rotation of the braid monodromy around the boundary of the disk. So like if you have just a braid that consists of full twists, then the number of twists is going to give you this then twist coefficient. And what I can prove is that if this fractional twist coefficient is greater than 1, then theta is non-zero for any braid with any number of strings. Again, before I go to the proof, I would like to say for people who are familiar with contact geometry, maybe not familiar, this is parallel to the story that's known in the open books context. There's, for contact structures, there's an invariant in Hager-Flare homology that is just a contact invariant of the contact manifold. And if you're looking at this fibration perspective, the open books perspective on the monodromy, there's a similar theorem due to Honda-Kazes matches that says that if you have a surface page of the open book with connected boundary, then if this quantity, the fractional twist coefficient is at least 1, then the contact invariant does not vanish. So this is known. But that proof uses a lot of information from sort of 3- and 4-dimensional topology, because to prove that you go through truth foliations. You say if you have an open book like that, you can make it compatible. You can find a truth foliation that's compatible to the open book. Your contact structure comes as a perturbation of a truth foliation, and then it has a symplectic filling. And then there's a non-vanishing theorem for contact invariance if you have a symplectic filling. And then you cannot use Zemo2 coefficients. You have to use twisted coefficients. So somehow it's both a proof that uses a lot of geometry, and it gives you a more complicated answer. This theorem we'll see in a moment. You can just look at those grid diagrams and do some combinatorics with braids, and it works out. I would be very interested to sort of turn this around and say this invariant tells you something about truth foliations, maybe a knot complements or something, but I don't know how to do that. So I promised Braid orderings and I promised a proof. So let's try to do that.
Can I ask you a question?
Sure.
Is a similar thing known, or do you know a similar thing for the distinguished element in the quantum homology?
That's a very good question, and the remark I actually wanted to make. I secretly set out with this right variance story because I wanted to find the geometric meaning of the Kavanagh homological invariant. And I failed. I have counterexamples to these two statements in Kavanagh homology. They're pretty easy to find just to kind of look around and use some computational programs. So in particular for 3 braids, we will see in the proof that kind of a key building block for the proof will be this braid that I've drawn. Right. So 2 strands go straight, and then the third one twists around positively once. And turns out that for 3 braids, kind of the proof follows from just considering this kind of example where this goes straight, and then you can add any number of negative crossings. So it turns out this is a right variant braid. This is not necessarily positive or quasi-positive or anything if you have a lot of negative crossings. And this invariant is non-zero, but the Kavanagh homological invariant is 0. And then you can show that you can find examples where this number is as big as you want, and you still have a vanishing invariant in Kavanagh homology. So that would be interesting to me to have some non-vanishing theorem, but I don't know. Any more questions? So let me digress a little bit and talk about Braid orderings and the relation to this right-varying, non-right-varying story. So this is the fact that's probably known to a lot of people, that the Braid group Bn is orderable. So what's an orderable group? It means you have a linear order that is compatible with the group operation. So this is maybe left invariant as you look at the product operation. And so how do you know that this is orderable? This is actually an interesting historical question, because I think if you sort of look at published works, the first linear order on the Braid group was described by Noir in terms of just algebra of the Braid words. But then this was sort of probably secretly known to a lot of people around Thurston, definitely Thurston himself, from, again, the monodromy perspective that we're going to see, just that sort of nobody cared to write this down. And it's the interplay between the geometry and the combinatorics of the Braid words that will be useful to us. So let's see why this is clear from the monodromy perspective. Let me just define that the element gamma of the Braid group is greater than the identity if gamma is right here. Right? And then I can define that beta 1 is greater than beta 2 if beta 1, beta 2 inverse is greater than the identity. This is pretty much forced on me by the left invariant property. Okay, and why is this a linear order? Well, you can check. It's pretty clear that sorry, I'm saying something. I'm saying something stupid. I didn't mean to say this.
Sorry, do you mean beta 2 inverse beta 1?
I mean that you don't look at whether it's right here. I mean that you look at this arc, this one arc. I made a mistake.
Is it left or right invariant?
This is right. Okay.
Okay.
You know, it doesn't matter which side you choose, because it goes to the two can be switched by doing conjugacy, but you can never say it's invariant under both, because you can't really apply that it's conjugacy. Okay. So I can't do that this is right here. I wanted to say it's completely obvious that any Braid is either greater than 1 or less than 1. If I say right here, it's not going to be true. But what I do is I look at this particular arc. So let's look at this particular picture of the disk where all the points are lined up in order, and let's take this one arc, and let's say gamma is greater than the identity if this arc, maybe A0, goes to the right, under the action of gamma. Right? So then you can say, well, any Braid monodromy will either turn this arc to the right, left it the same, which is fine, which is still, or
We need to think about like.
I'm sorry. I need to look at this entire line, and then I need to say that the image of this line should go to the right. Okay, now this is clear. If L goes to the right. So, okay, so now finally it's clear that this L either goes to the right or goes to the left, how do I decide? Well, so I start looking from this point, and if this first arc goes to the right and goes to the left, I'm good. If this arc is staying put, then I look at the action of the next arc. So the first time that you veer from just going straight along this line is telling you whether you go to the right or go to the left. And unless you are the identity, you're gonna eventually go to the right or go to the left, right? Okay. Then, if you have two braids that go to the right, you compose them. Of course, they're gonna still send this arc to the right. And this will tell you that you have transitivity on this linear wall. So it's pretty easy to check that this is well defined and that satisfies the properties and the invariance and everything. So this is one way to define the ordering. The algebraic approach is to look at the braid words. So first let's define sigma 1 positive braid words. So this is, if you look at the braid word, this means that sigma 1 comes with positive exponents only. So you can have something like sigma 1 cubed, sigma 2 inverse, sigma 5, sigma 1, whatever. So other generators can come with any exponents or not come at all, but sigma 1 should appear with positive exponents and non-zero, it should actually appear. Right? You say that you're sigma 1 free if no sigma 1, and if you're sigma 1 free, you want to look at sigma 2 positive. You want to say, well, maybe I have a braid word where there's no sigma 1 and sigma 2 comes with positive exponents. Okay. And then if you have no sigma 1, no sigma 2, you look at sigma 3 positive and so on. So all of these sigma I positive define something that's called sigma positive braid word. And you define that the braid is greater than the identity if it can be given by a sigma positive braid word. So I think if you look at this definition and try to interpret what does it do geometrically, if you have a sigma positive braid word, well, it does exactly what we asked for here, because if you are sigma 1 positive, it means that sigma 1's only come with positive exponents, so the twisting on this arc will go to the right. If you're sigma 1 free, this arc will stay put, but sigma 2 positive means that the second arc will twist to the right, and so on. So one direction that this definition implies that greater than the identity in terms of this definition implies greater than the identity in terms of this definition. This is clear. Doing the converse is a little more complicated. You really have to stare at this monodromy and unravel it and do a lot of kind of tedious work. And also for Dernoy, it was kind of a big theorem, because from this perspective, it was not obvious at all why you get a linear order, why every braid admits either the braid itself or the inverse can be given by a sigma positive word. Why do you have the properties? Why do you have transitivity? So this is not trivial from the algebraic perspective. But now the upshot of the story for us probably is this. So now suppose we have a braid which is non-right clear. Well, it means that it twists some arc to the left. I can look at the conjugate, it's not going to change my closed braid, it's not going to change my transverse knot. I can look at the conjugate and require that this particular arc goes to the left. And so then, if you believe the equivalence of the two definitions, I can say that any non-right wearing braid it has a conjugate that is sigma 1 mirrors. So simply put, you have a braid diagram which only has negative crossings up to. You don't only have it for the rest of the diagram, but here you only have negative crossings in the top. And then every right wearing braid just has every conjugate that's given by sigma 1. Has a conjugate. So now we are all set. Given this, we can show that the invariant theta vanishes for non-right wearing braids. And also you can use exactly the same proof for Kavanagh homology. This is from Grigg and Baldwin. So what do? You say, I'm a non-right wearing braid, I can have a braid rod of this form, and then I just have to deal with these negative crossings. And you use the fact that not for homology and Kavanagh homology also is functorial under not cobordisms. So if I maybe get rid of a crossing, then this gives me a cobordism between knots, and this gives me a map on knot homology. And if this is a positive crossing that I'm getting rid of, by the way, I forgot to say I'm also slightly cheating. Everything is for sort of mirrors. This theta lives in the mirror homology. And the diagram approach that I described also gives you mirror homology. So anyways, assuming that this is about mirrors, the invariant theta of this knot is mapped to the invariant theta of this knot. And similarly for the Kavanagh homology. And of course, getting rid of the positive crossing, you can say that this is the same as starting with sort of two straight strands and adding a negative crossing, because you can do the second Rodemeister move and introduce the positive and negative. So now I have a lot of negative crossings. And I know that the invariant theta of something that has negative crossings at this row, something that's non-right wearing, comes from the invariant of the braid, where I would get rid of all the crossings except one. So I would have this one negative crossing up top, and then whatever other braid. And this is called the transverse stabilization and transverse knot theory. And even if you don't know much about transverse knots, you see that this is a kind of model thing that you can compute, and it's known in non-for homology and also in Kavanagh that on this side you get 0. So on this side you should also get 0. So this is this kind of functorial property, tells you that. And now I need to tell you how to prove this non-vanishing result, and finally maybe to get to use this diagram. So I can also reduce the discussion to some model that I have to study. So let's see, if I have this C greater than 1, it means that I have, sort of roughly speaking, means that I have more than one full positive twist of rotation around the one. And this means that if C greater than 0, my braid beta can be represented as a full positive twist on all strands times some right veering braid. And if it's right veering, then I can say this is going to be the sigma 1 positive or sigma 1 free. So I can say that my braid looks like this. I have this one positive twist. And then I can guarantee that on this level, there are maybe some positive crossings, maybe no crossings at all, but there are no negative crossings. Okay. And what happens here at the next level, sigma 2, sigma 3, and so on, I don't know. There might be positive crossings, there might be negative. But then, remember, we had this functorial property. If you can put in more negative crossings and prove non-vanishing of the invariant, then we will have non-vanishing of our braid. So if there are some positive crossings here, let's get rid of those. So there are no crossings on this level. So this one strand that just goes around, doesn't get involved in anything else. And let's say all that we have here just has negative crossings. So the kind of the worst case scenario. So we have negative crossings here, and let's say there are some full negative full twists on strand this way. So maybe key negative full twists, and this is instance. So now we can say that any braid that we start with, anything that has this form, we can introduce more negative crossings into the braid so that it will become a braid of this form. So it suffices to just show that the invariant theta does not vanish with these braids beta and theta. So this is if C greater than 0 for a braid of any index. For 3 braids, you essentially get the same model calculation. The thing is, you don't have to require anything because you can go to just sort of Murasugi classification and go in and check things. And you also get that the only braid that you really need to compute is the braid with this a lot of negative crossings and one full positive twist around. So I want to show you this is not.
So is it C greater than 0 or greater than 1?
This is C greater than 1 here because I need one full positive twist that I'm using, and then the rest has to be right here. So I can't even say C greater or equal than. Oh, this is.
Okay.
Thank you. I see 1 over there. But here it's actually greater than 0. Here, anything that's right veering works. And now the punchline is that to prove this fact, to prove this non-vanishing, I can just do this model calculation, and the model calculation turns out to be easy to do via grid diagrams. This is the grid diagrams, and this Thurston invariant was very, very effective to just kind of get ad hoc examples. This knot is different from this knot. It's sort of funny that you can actually prove a general statement, a rather general statement, using this grid diagram approach. So I claim that this is a grid diagram for one of the braids like that. It's 3 strands. And before I draw the braid, before I actually overload this picture with more information, let's look at this invariant. Let's convince ourselves that it's non-vanishing. So why would it be non-vanishing? Well, these points are the points that I care about, and I claim that there are just no empty rectangles that could kill this point, that could go to this point. And I know it's a big diagram, but if you kind of stare at this, I need to find something. And these O's are strategically located so that I can't really make anything that is wider than just height 1. And height 1, well, you go around, you sort of want to go to this point, but you hit an X every time. There's this pattern, right? See, OX, so these pairs of X's and the O's here, and it kind of creates the situation. And the corners that fall out of the pattern a little bit don't do anything to this argument. You just really examine the diagram and you see that there are no empty rectangles going to this point. So this is essentially the proof of the non-vanishing. And then if you can't immediately see why this is that knot, let's try to draw it. So first, let me connect like this. And this green strand that I'm drawing is that strand that goes straight, not interacting with much else. So it does interact winding around just once if I connect these other strands. So here you see the green strand just twists around the purple part exactly once, and then it just goes, not doing anything else, goes around, not doing anything else. And these 2 purple strands are gonna interact by creating all the negative twisting. So again, I have to connect here. And this is what you see from the diagram. I have a lot of negative crossings. So that's essentially the picture. So this is the correct braid, and then just somehow this extra strand plays this protective role and rules out all the rectangles that might kill your special generator. For a bigger number of strands, there's a similar pattern, a very similar diagram, just that I don't want to draw it. I think this is pretty much
Questions? So, is there, I know that psi is related to sort of the double branch cover of your transverse knot. Is there any relation between theta and invariance of the double branch cover?
Well, somehow for the 3 braids, you get something just if you go around, not directly. There's no direct relation that I know of, and I don't know how you would get it, how you would relate theta invariant to the branch double cover. For 3 braids, just going around here, you can say if this is non-zero, if and only if the braid is right-veering, and the braid is right-veering if and only if the upstairs, the open book is right-veering, and the open book is just a torus with one boundary component, so it's right-veering if and only if it's tight, and non-invariants, hair floor invariants do not vanish. So somehow for 3 braids, you get this relation, but it's probably not very deep just because it's kind of a coincidence.
I have one question. When you define the special cycle, you can choose the O's instead of the X on a distinguished component, say the blue one, to the dot on the top right of U instead of the top right of the X.
So you have to be a little careful. I think so there's this asymmetry between what's O, what's X, and I never remember this off the top of my head, but it's something like orientation reversal of the knot or orientation reversal of your manifold or something. When you're looking at the Legendre transverse picture, you have to be careful because this is kind of a sign of stabilization that's important. In the Braid picture, you can do positive stabilizations, you can't do negative stabilizations. And you can really get something that's not an invariant. Is that?
Didn't understand. I mean, if you switch the O's and the X's,
Yes.
then in this tilde,
Yes. Do you get?
you don't change anything. I mean, this is responsible for the orientation of the
Yes.
knot component.
Right.
But
The transverse you don't, because I don't remember. Some things you can do and some things you cannot do. You just get zero, because the transverse stabilization becomes.
Well, yeah, you cannot. So you change if you do transfer stabilization, but if you flip the O's and the X's, you don't do that.
So I can
you
just go
reverse the
to-
orientation of the knot, but this guy doesn't see that.
The answer is actually that you can, but you have to check these things carefully every time. There's the danger that you've done something that you didn't want to do.
Is it possible to make sense to extend this invariant to more general situation, for example, inside an open book?
So this, as I mentioned, this is what was done by Lisk and Stivcic for the situation where you do have just a transverse knot, the Legendre knot in a general contact manifold, and you can find a compatible open book, meaning that you can put your knot on the page and then you can use Kegel diagram decomposition of this picture and define the invariant.
You also have vanishing result?
But this is a good question. I don't know how to prove vanishing result, and so there are two sides to this. Could I prove the vanishing result without the combinatorics in the more general situation, even just with 3 braids, but just not using grid diagrams, but using other tools? And I don't know how to do that. Another thing that I tried really hard would be to reprove the result in the open books situation for contact manifolds, because there's no direct proof for it. For the analog of this, you have to use foliations, you have to use symplectic fittings. Can you just look at the diagram and do something directly? Maybe there's a convenient basis in the mapping class group, and I don't see it. Maybe it can